Hello. In this lecture we will explore a new topic, the topic of cookies. Cookies are a way to mitigate CPU exhaustion and potentially falling a victim to a denial of service attack. Or yes, becoming a participant in a denial of service attack. So, one of the things that is different between IKE version 2 and IKE version 1 is the fact that the Diffie-Hellman exchange happens in the first two messages. The first message from the get-go sends the Diffie-Hellman key. The intention was to reduce the number of back and forth messages needed to establish an IKE connection. However, malicious attackers can use this against IKE version 2 in one of two ways. The first way is sending a large number of IKE init messages to a VPN gateway. This can be from a spoofed source address that doesn't exist. Every time the VPN gateway responds to an IKE init message, it will create the Diffie-Hellman key and run the Diffie-Hellman calculation to produce the master key. This is computationally intensive, and if a large number of messages gets sent to the gateway, this potentially would lead to high CPU utilization and potential exhaustion of system resources, preventing the system from responding to legitimate SA init messages. To combat this issue, the RFC devised a way for the VPN gateway to respond to a large number of IKE SA init messages with incomplete IKE auth message. Those are called half-open IKE sessions. The VPN gateway should, upon detecting a large number of half-open connection, instead of going through calculating the Diffie-Hellman keys and exhausting resources for no reason, the gateway would just send a cookie message. It will send an informational message of type notify with a message type of 16390, specified in the RFC. This cookie consists of a secret made up by the responder. This could be anything, making it a random value. It will create that secret, it will concatenate it with the nonce initiator, SPI of the initiator as well as the IP address of the initiator. It will calculate the hash of that string, which is the concatenation of the nonce initiator, the IP of the initiator, in addition to the SPI ID of the initiator, concatenated with the secret. It will create a version number for this secret. This number increments. The version of the secret increments. This value is used to keep track of the number of cookies and secrets sent to a specific IP address. So, instead of running an expensive Diffie-Hellman calculation, the responder just creates a random secret and keep it in its cache. If this IKE was sent by a malicious attacker, there will be no response to the cookie notify message. This would result in the responder abandoning that session. End of story here. Okay, what if this was a valid initiator, an actual initiator that is trying to establish a session? In this case, the initiator would return a cookie as well. Now, notice that up until that point that the actual message 1 gets received with the cookie matching the cookie of the responder. Only then, the responder allocate a responder SPI number, further reducing the overhead of dealing with spoofed IKE attempts. So, there will be an additional request-response pair. If you remember with a normal negotiation, what happens is that there are two pairs of messages. Message 0 pair for IKE SA init and message 1 pair for SA authentication. The overhead of adding the cookie process resulted in an additional message pair. So instead of the auth being with message ID 1, it's message ID 2 now. Okay. The second use for cookies is to keep track of the number of half-open messages from an IP address. If there are a lot of connections half-open from a specific IP address, the IPsec stack can be configured to ignore the messages from that address. This is done to avoid sending lots of responses to a victim device. Usually denial of service flooding intention is to use one party to attack a different victim, taking themselves out of the loop. This makes denial of service difficult to prevent. Now, finally, that won't prevent someone from sending thousands of IKE requests from thousands of different IP address. In that case, there is a potential of a denial of service on that VPN gateway, in that, I mean the responder. However, no other victims will be harmed in this attack. Usually, whenever a VPN gateway detects a large number of half-open attempts from a wide variety of IP addresses, that gateway would start mandating cookies on all the sessions to fend off such a sneaky attacker. Hopefully you enjoyed this lecture. We will discuss more in the next lecture.